In the previous lectures, we have dealt with forces which act on a point. So, for example, I took a mass on which a force was acting. Then we took trusses and dealt with forces acting on the joints of the trusses. So, for example, the one force could act here, one force would act this point, one force would act at this point, and so on. Similarly, when we considered frictional forces, we considered the forces as if they were acting at one particular point. However, in nature the forces are distributed. For example, if I take an extended body and consider the gravitational force on it, on each point there is a force acting. Its net effect is felt at a certain point which we know as the center of gravitation. Similarly, if I take a plate submerged, say in water, the force acting on it due to the pressure of water is also distributed. Not only it is distributed, its magnitude is different at different points. So, deeper you go, larger it is. Near the top, the force is not that large. So, these are the arrows that are showing the force due to the pressure. This is also a distributed force which varies with the depth of water. And now, we want to develop mathematical techniques to deal with such forces. In this lecture, I am going to develop concepts such as centroid of an area which is related to the first moment of area, and then see how these concepts can be applied to mechanics or statics in particular. So, let us start with the concept of the first moment of area. I am first going to give you the definition, and then later we will employ it in certain statics situations. Suppose I am given a plane area like this in a coordinate axis set x and y. I define the first moment of this area m x about the x axis as summation y I delta a I, where delta a I is a small area here, delta a I at a distance of y I from the x axis. So, what am I doing? I am taking small elemental area delta a I and multiplying it by the distance from the x axis and summing it up. In a continuous distribution, you know from your course in calculus, this is nothing but y dA. That is the first moment about the x axis. In a similar manner, we define the first moment about the y axis. This is the area, and I took a small elemental area here at a distance y I from the x axis and a distance x I from the y axis. This is x axis, this is y axis. Define my first moment about the x axis as y dA, and similarly I can define m y, that is the first moment about the y axis, as summation x I delta a I, which in the limit of continuous area becomes x dA. These are the definitions. So, we have first moment about the x axis and first moment about the y axis. Using the concept of first moment, I can define the centroid of this area. Centroid coordinate x coordinate x c is defined as first moment about the y axis divided by the total area, which is summation x dA divided by A, and similarly the y coordinate is defined as mx divided by A, which is summation y dA divided by A. Now, let us do certain examples using these definitions to calculate these quantities. As the first example, I take a triangle one corner of this triangle is at the origin. This is the x axis, this is the y axis. The height of the triangle is h. This distance of the vertex from the y axis is a, and the other corner is at distance b. I wish to calculate its first moment about the x and y axis and its centroid x c and y c. So, let us do that. Let us first calculate x c, which is related to m y divided by the total area, which is equal to integration x dA over the total area. To calculate x dA, or the moment about the y axis, let me take a small area dA like this parallel to the y axis. This distance I will take to be dx. The height of this is y. From similarity of triangles, I know that h divided by a is going to be equal to y divided by x, and therefore, y equals h over a x. This is true as long as x is below a. For x greater than a, I take a small area here whose y is going to be different, and that also we can calculate. Let me now go on to the next page, so that calculations become more clear. So, this is the y axis, x axis, this is the triangle, this is b, this is a, this is h. One strip I took here, other strip I am taking here. For the first strip, I know that y divided by x was equal to h over a, or y equals h over a x, x less than equal to a. For the second strip, I am going to have this distance is x. So, I am going to have y divided by b minus x, that is this distance, y divided by b minus x is going to be equal to h divided by b minus a. B minus a is this distance, and therefore, y equals h over b minus a times b minus x. Now, I am ready to calculate the moment about the y axis. The moment about the y axis, my is equal to integration x dA, which I am going to write as integration x y dx, where y dx represents the area of this strip or this small strip. This I am going to divide into two parts, because behavior of y with respect to x is different for x up to a and for x greater than a. This, by the way, is for x greater than a. So, I am going to write this as integration 0 to a x y up to a y is h over a x dx plus a to b x h over b minus a b minus x dx. That is m y, and you calculate this, the integrations you can perform easily. You get an answer for m y. Let me make the figure again. This is b, this is a, this is the height h, this is the x axis, this is the y axis, and for m y, which I wrote as 0 to a x h over a times x dx. Let me see, I indeed wrote h over a, yes, and plus a to b x h over b minus a b minus x dx, and when you do this integration, it comes out to be h b divided by 6 times a plus b, and therefore, x centroid is equal to m y divided by the area, which is h b over 6 a plus b divided by h b divided by 2, and this comes out to be 1/3 of a plus b. That is the x coordinate of the centroid of the triangle. Let us now calculate the y coordinate. Again, I make this triangle x y b a h, and to calculate the y coordinate, I take the elemental area dA like this. Recall that y c is equal to m x divided by the area, which is integration y dA divided by the area. So, at a height y, I take this is small strip multiplied by y and then calculate the area. You can see from similarity of triangles that I am going to have y h minus y, this is h minus y divided by h is equal to the width of this strip, which let me call delta x, divided by b, and therefore, delta x is equal to b h minus y divided by h. This is the length of this strip, and therefore, we can write, make the picture again. I am taking this strip, I am not writing b and a this time. We got h minus y divided by h equals delta x divided by b, and m y or m x is going to be equal to y dA, which I can then write as y delta x dy, y varying from 0 to total height h, and this comes out to be y delta x is b over h minus y dy, and you do this, this comes out to be b, y varies from 0 to h, this comes out to be b h square over 6, and therefore, y c is going to be m x divided by the total area, which is b h square divided by 6 over b h divided by 2, which comes out to be h over 3. So, we have calculated the centroid of a triangle, and what is it? It is for a triangle which is given like this, with this distance being b, this being a, this height being h, the x, y, the x coordinate is 1/3 of a plus b, and y coordinate is equal to 1/3 of h. You can see that y coordinate is 1/3 of the height and x coordinate is 1/3 of b plus a. So, suppose I had a triangle like this, an area which is triangular of this shape. In that case, a and b are going to be the same, so that x c in this case would become 2/3 of b or 2/3 of a, and y c is obviously equal to h over 3. So, we have calculated the centroid for a triangle. As a second example, let me take a semicircular area like this of radius r. So, obviously, its diameter is 2r. This is the x axis, this is the y axis, and I wish to calculate its centroid. From symmetry, you can make out that the centroid must be on this axis somewhere, but I want to explicitly calculate it to show you how to do it. So, again x c is going to be equal to m y over the total area. To calculate m y, we do integration x dA over the area. To calculate the dA, I take a strip like this, which is a vertical strip at a distance x from the y axis. You can see that dA in this case therefore is going to be the area of this strip, which is y dx, and therefore m y is going to be integration x y dx, x varying from 0 to 2r. What about the value of y at a given x? The equation of the circle whose center is at r and y 0 is going to be x minus r square plus y square equals r square, and therefore, y is equal to square root of r square minus r minus x square, and therefore, m y for the semicircle area is going to be equal to, this is 2r integration x y is square root of r square minus r minus x square dx 0 to 2r. Let me take r minus x to be equal to r sin theta, so that x equals r minus r sin theta. In this case, dx is going to be equal to minus r cosine theta d theta. Substituting this, we get m y equals, when x is 0, Sin theta is going to be 1 and therefore theta is equal to pi by 2. When x equals 2r, sin theta is going to be minus 1 and therefore this is going to be minus pi by 2. X is r 1 minus sin theta, x equals r 1 minus sin theta times r square minus r minus x square is going to be r cosine of theta, and then for dx I have minus r cosine of theta d theta. Because of this minus sign here, I can write this as minus pi by 2 to pi by 2 r cubed cosine square theta minus sin theta cosine square theta d theta. This is a simple integration which we can perform. So, I have my for the circle or semicircle of diameter 2r my equals integration minus pi by 2 to pi by 2 r cubed cosine square theta minus sin theta cosine square theta d theta. Cosine square theta sin theta is an odd function with respect to theta, and therefore, this integration sin theta cosine square theta d theta minus pi by 2 to pi by 2 is going to be 0, because as you go from theta to minus theta, this integrand changes sign, and integration cosine square theta d theta minus pi by 2 to pi by 2 comes out to be 1 plus cosine 2 theta over 2 d theta minus pi by 2 to pi by 2, which is nothing but pi over 2. And therefore, we get my is equal to pi over 2 r cubed, or x c, which is my divided by the area. Area is pi r square by 2. So, pi r cubed divided by 2 divided by pi r square by 2 equals r. So, as we noticed earlier, the x coordinate is on this axis. This is r. How about the y coordinate of the centroid? Let us calculate that. To calculate the y coordinate, I take a strip like this at a height y. So, y c is nothing but m x divided by the total area, which is integration y dA divided by the total area. Y dA, you can see, is going to be equal to the area of this strip here, this one, times the y. This strip area is going to be this if this distance is delta x dy, and y varies from 0 to r. To calculate the value of delta x, we again use the equation for the circle, x minus r square plus y square equals r square, and that gives me x minus r is equal to plus or minus the square root of r square minus y square. I get two values of x, namely x 1, which I have shown here, equals r plus minus the square root of r square minus y square, and x 2 which I have shown here, which is equal to r plus square root of r square minus y square. And therefore, delta x, again let me make this figure. This is x 1, this is x 2, delta x is going to be x 2 minus x 1, which is equal to 2 square root of r square minus y square. Remember, we are after m x, which is equal to y delta x dy, which in this case is therefore going to be 2 integration y square root of r square minus y square dy, y varying from 0 to r. Let us take y equals r cosine theta, so that m x becomes equal to 2 integration 0 to pi by 2 r cosine theta times r sin theta times dy is r sin theta d theta. So, we have this is m x equal to integration 2 0 to pi by 2 r sin theta r sin theta r cosine theta d theta, which is 2 r cubed integration 0 to pi by 2 sin square theta cosine theta d theta. Cosine theta d theta is d sin theta. So, I can write this as, by substituting z equals sin theta, I can write this as 2 r cubed 0 to 1 z square dz, which is 2 r cubed divided by 3. That is m x, and therefore, x y centroid, which is m x divided by the total area, is going to be equal to 2 r cubed over 3 divided by pi r square by 2, which is nothing but 4 r over 3 pi. Therefore, if I look at this semicircle, the semicircular area, its centroid is at a distance r and at a distance at a height of 4 r over 3 pi. Slightly 3 pi is roughly 9. So, 4 r 3 pi is slightly less than r by 2. So, it is somewhere here. This is x c y c. Having defined the centroid of a plane area and solved 2 examples, let me make a point about the centroid of a plane area, and that is that the centroid of a plane area is fixed with respect to the area. That means, no matter which coordinate system I calculate the centroid in, it will always come out to be the same point in the body or in that area. So, centroid of a plane area is fixed with respect to the area. And let us see how we can prove this. So, let us take 2 set of axes x y with origin O and another set of axes x prime y prime with origin O prime. The O prime is shifted with respect to O by x coordinate A and y coordinate B. Let the centroid coordinate in O prime frame be x c prime, which is equal to x dA over the area, or rather x prime, and similarly y c prime is equal to integration y prime dA over the area, where dA is some small area given in this plane area which I have drawn here. Now, let us calculate x c, which is equal to integration x dA over the area, but I know that x equals a plus x prime, and therefore, x c is going to be equal to a plus x prime dA over a. A dA integral, a comes out and integral dA is the total area. So, this will come out to be a plus x prime dA over a is nothing but x c prime. So, you see, if I calculate the centroid with respect to a shifted coordinate system, the centroid shifts by appropriate amount, so that remain at the same point in the body. And similarly, you can show that y c will be equal to b plus y c prime, which I leave as an exercise for you. As an important observation about centroids, let us now take an area which is made up of 2 or 3 simple plane areas, let us say a square, a triangle, and a semicircular planar area. So, there is one kind of area, here is another kind of area, and here is the third kind of area, but all of them are joined together. Then it is very simple to prove that if I want to calculate the centroid of this whole system, then x c of the entire system would be equal to the area of system 1 times its centroid plus area of the second area x c 2 plus and so on divided by the total area and so on. That means, in this case, if I consider the square to be area 1, then x c 1 is known. Similarly, if I take semicircle to be area 2, then x c 2 is also known, because we already calculated it, and x c 3 for the triangle is also known. I also know the formula for 3 shapes, and therefore, can easily calculate the centroid for the entire system. Similarly, y c for the total area is going to be a 1 times y c 1 plus a 2 times y c 2 plus so on divided by a 1 plus a 2 plus a 3 and so on. This comes in handy when we know several areas that are joined together, and I know the formula for different areas, but wish to calculate the centroid for the joint area. Let us do a couple of examples using this. I leave the simple proof of this for you to do. So, as the first example, I take a square and join on it 2 triangles, equilateral triangles, one here and one here. I wish to calculate the centroid of this assembly. Let me call this number 1, let me call the triangle here number 2, and let me call the red triangle number 3. Then I know that x c 1, that is the x coordinate of the centroid of the square, is going to be, if this side is a, is going to be a divided by 2. Similarly, the height of this triangle, because the side is a, is going to be a root 3 by 2, and therefore, x c 2 is going to be equal to a plus the distance of the centroid from the base, which is nothing but 1/3 the height, and therefore, a divided by 2 root 3. And xc3, that is the x coordinate of the centroid of the third triangle, is going to be right on the dividing axis, and which is going to be a by 2 again. And therefore, x c of the entire assembly is going to be equal to area of the first square, which is a square times a by 2, plus area of the second one, which is going to be equal to the base, which is a, times the height, which is a root 3 by 2 divided by 2, that is the area, times xc2, which is a plus a divided by 2 root 3, plus the area of the third one, which is a by 2 a root 3 divided by 2 times a by 2 divided by the total area, which is a square plus a by 2 times a root 3 by 2 plus a by 2 times a root 3 by 2. That is the formula for xc. And you calculate this, this comes out to be about 0.594 times a. By symmetry, yc would also come out to be the same, and therefore, for this assembly, where I have a square of side a triangle, equilateral triangle on top and on the side, this is a x y, I get x c to be, which is summation a I x c I, I am writing a general formula, divided by summation a I, which is comes out to be 0.594 a, slightly to the right of the centroid of the square, which is expected because of the area added onto the right, it shifts to the right, and similarly you can calculate yc is going to be come out to be again 0.594 a. So, this is how you use this observation, that if I want to calculate the centroid for an assembly of plane areas for which I know individually where the centroid is going to be, I can calculate the centroid for the total assembly. Let me take another example where I have an area formed by taking away a semicircular area from a square of side A. So, I wish to calculate the centroid of the shaded area, where the shaded area has been formed by taking away a semicircular area from a square of side A. Again, I can use the same theorem, but in a different way, because now what I am going to say is that x c of the square, which I already know is going to be right in the middle, is going to be equal to x centroid of the shaded area plus x centroid of the semicircle. And therefore, if I wish to calculate x shaded of the, this is area of this square, area of this square is going to be equal to x c of the shaded area times area of the shaded area times the area of the semicircle. Right, sorry for that. So, area of the square times the centroid of the square is going to be equal to area of the shaded area times the centroid of the shaded area plus x c centroid of the semicircular area times the area of the semicircle. And therefore, x c of the shaded area is going to be equal to a square times xc of this square minus xc of the semicircle times area of the semicircle divided by the area of the shaded portion, which is going to be area of the square minus area of the semicircle. And that is what we wish to calculate. We have already calculated that for a square, xc is going to be a by 2, where a is its side. The radius of the semicircle is equal to a divided by 2, and I know from the base we already calculated this, the centroid is at a distance of 4r divided by 3 pi, and therefore xc with respect to this origin of the semicircle is going to be equal to a minus 4 over 3 pi times a by 2, which is a minus 2a by 3 pi. This is the xc of the semicircle. So, now we are all set. I know xc for the square, I know xc for the semicircle, and area of both, area of square is equal to a square, area of semicircle is equal to pi by 2 times a by 2 whole square, and therefore, I can calculate the xc for the shaded region from the formula that we derived earlier, and xc comes out to be, you plug in the numbers, 0.314 a. Notice that if I had removed an entire this half, let me make it with blue, if I had removed this half blue of the square, the xc would have been here at 0.25 a, but because of this extra area which I am showing here to the right, the centroid shifts slightly to the right and is at 0.314 a, which is greater than 0.25 a. That would have been the case if I had removed this entire half of the circle. Y coordinate, obviously because of the symmetry, remains at a by 2. So, I have given you two examples of how to use the observation that the centroid of a given area is actually a weighted combination of centroids of the areas making this joint area to calculate centroids of complicated shapes. Having given you the concepts of first moment of an area and the concept of centroid, we are now ready to apply these concepts to mechanics. So, the question we ask is, suppose I have a beam on which I do not apply force at a certain given point, but the force on it is distributed. So, there is some force per unit area. Let me show this by a graph, per unit length. So, there is a force acting at each point. Let me call this function f x, so that if I take a distance, a small section of length delta x here, the net force acting on this point delta f is going to be given as f at x delta x. What we wish to now find is what is the net force acting on this beam and where does it effectively act. That means, if I were to suppose apply an opposing force to balance it, where should I apply it so that this force is balanced? The answer comes in terms of the quantities just defined. So, if there is this force f x, distributed force acting on it, the beam, the net force F is going to be summation delta F, which is nothing but integration, or let me write it one more step with summation. Delta F is nothing but f x delta x, and this is nothing but integration f x dx, which is the area under this curve. That gives you the total force for a distributed force per unit length given. How about the moment or the torque created by this force? That is obviously going to be x delta f integrated, which is nothing but x f x dx. This is the torque. If I want to calculate apply an opposing torque with a point force, that force has to be equal to the net force which is being applied, which is the area of this curve, and it has to be at a point x, which is nothing but integration x f x dx divided by integration f x dx, which is nothing but the centroid of this curve that describes force per unit length. So, we can say that effectively the force acts at the centroid of this area, this given area which describes the force distribution. So, you see immediately the connection between the first moment or the centroid that we define with a problem in mechanics. As an example of things to come, let me end this lecture by solving a problem of calculation of the center of gravity of a rod made of two different materials. So, we take a rod which is made of two different materials. One material here is of length L1 and its mass per unit length is lambda 1. The other rod here is of length L2 and its mass per unit length is lambda 2. We wish to calculate its center of gravity. Starting from this point, let us say this is our axis, so that this is our x axis, this is our y axis, or on the y axis I will be showing the load, and this is x equal to 0. Let me go to the next page and show this rod, black here, of length L1 and blue part for the other length L2, L1 mass per unit length is lambda 1 here, lambda 2 here. My axis is starting from here and going this way. If I plot the load curve, it will be constant lambda 1 g per unit length here, and if we assume lambda 2 to be greater than lambda 1, lambda 2 greater than lambda 1. And I wish to calculate the center of gravity. By definition, the center of gravity is the centroid of this load curve. So, this is going to be lambda 1 g is the load per unit length on the first part times x dx integration 0 to L1 plus integration L1 to L1 plus L2 lambda 2 gx dx divided by the total area, which is going to be lambda 1 L1 plus lambda 2 L2 times g. You see, g cancels from the denominator and the numerator, and I am left with the center of gravity of this rod L2, L1, lambda 1, lambda 2, and let me again show you the load curve is something like this. The center of gravity is 0 to L1 x lambda 1 dx plus L1 to L1 plus L2 lambda 2 x dx, g we have already cancelled, over lambda 1 L1 plus lambda 2 L2, and this comes out to be lambda 1 L1 square divided by 2 plus lambda 2 1 over 2 L1 plus L2 whole square minus L1 square divided by lambda 1 L1 plus lambda 2 L2. You simplify this and you get x c, which we just calculated to be 1 half lambda 1 L1 square plus 1 half lambda 2 L1 plus L2 square minus L1 square over lambda 1 L1 plus lambda 2 L2 to be 1 half lambda 1 L1 square plus 1 half lambda 2. I can simplify this. This will come out to be 2 L1 plus L2 times L2 divided by lambda 1 L1 plus lambda 2 L2. So, from the left hand side end of the rod, this is where the center of gravity lies. We can also calculate the center of gravity by using our observation earlier that if there are two different areas given, the center of gravity can be calculated from those two if I know the center of gravity of each one of them. So, if I were to use that, you see the load curve on the rod is something like this. I know the center of gravity of this load, which is like here at a distance of L1 by 2, and center of gravity of the other load is here, which is at a distance of L1 plus L2 divided by 2. The total area here is lambda 1 L1, total area here is lambda 2 L2. So, x c is going to be x c 1, that is the first part, times area 1 plus x c 2 area 2 divided by area 1 plus area 2, and that is going to be L1 over 2 times lambda 1 L1, g would cancel from the top and the bottom, plus x c 2, which is L1 plus L2 divided by 2 lambda 2 L2 over lambda 1 L1 plus lambda 2 L2. So, we have calculated x c to be lambda 1 L1 L1 over 2 plus lambda 2 L2 L1 plus L2 over 2 divided by lambda 1 L1 plus lambda 2 L2, which is same as lambda 1 L1 square divided by 2 plus lambda 2 over 2 L1 plus L2 times L2 divided by lambda 1 L1 plus lambda 2 L2, which is the same answer as we obtained earlier when we calculated the center of gravity by integrating over the entire area. So, this is a simple example of how center of gravity is related to the centroid of the load curve. In the next lecture, we will be doing more such examples.